I'm mostly going to talk about Venus tonight, but if you are watching this on Zoom, there have been one or two changes just through the discussion over tea and coffee. So your slides might not look quite like these slides, but never mind. The image on the cover slide, is that the title slide, is from the Aral Sea, which is rapidly disappearing. And you'll see later on is the link between Venus's past and Earth's future. I should also highlight that last time I was here, I think I was still on Envision, which is the mission I proposed about, I don't know, 10 years ago or more now, that's going to go to Venus in the next 4 or 5 years from the European Space Agency. I was kicked off it by NASA. NASA have withdrawn, and I have rejoined Envision a couple of weeks ago, so I'm very pleased about that. But in the meantime, our space agency, UK Space Agency, funded me to work with the Indian Space Agency, who also have a mission to Venus going in the next 5 or 6 years or so, which through what we call the bilateral science program. So there's a lot of Venus things going on, and I believe somewhere over the pond they have a couple of missions as well, if they ever get off the ground. So why Venus, and what's it got to do with engineering geology on the Earth? Well, I have studied both for most of my career. I think as was just alluded to, I actually spent probably 20 years at Imperial or thereabouts as an undergraduate, as a postdoc in earth sciences, and then eventually I moved into civil engineering and worked on the engineering geology of London at the time. And that's also where I came to propose the Envision mission, and then had some children, bad mistake, and family commitments and everything else. The opportunity to go to Royal Holloway came up, and I moved there, which is much closer to where I live in Shepperton. And have been there about 7 years or so. But it was also one of the advantages is that actually I could wear both my hats together. So I can study Venus and engineering geology in my day job, which is very nice. Where's this all leading me? Well, the thing I find interesting about Venus is, as you can see from this slide, it's a bit probably clearer on my screen than this screen, but anyway, it's all green. It's not really green, it's orange, but it's all green because it's flat. Venus is a very flat planet. And when we think about Mars and you think about the deserts and all that sort of thing, you don't appreciate that Mars actually has a lot of topography, and the Moon has even more topography. Because small worlds don't resurface themselves. They don't constantly remake themselves. And so one thing you'll notice about Venus is it's very flat. Earth is very flat, but in 2 levels. Venus is only really 1 level. But they're also huge. Venus and Earth are 10 times the size of Mars, and even more so than Mercury and so on. And so I call these planets, and we're finding more and more of these sorts of planets around other stars, I call them Tellurian planets. Tellus is the Roman god of Earth, so it's the appropriate name to use, rather than terrestrial, which is the sort of more generic term for a rocky planet. And I've made it my interest to study the 2 Tellurian planets in our solar system to try and understand what goes on, how they're driven. And the first part of my talk this evening is going to cover the history of that, really, uncovering how our planets work. Because we kind of think we know how Earth works, don't we? I was going to ask you a question, actually, I forgot at the end of that slide. What's the smallest Tellurian planet? It's bigger than Mars, it's smaller than Venus, it's not in the middle. I'll give you that as a clue, but you could work it out. Because we kind of understand how Earth works through plate tectonics, don't we? That's how Earth works. That's how it loses its heat. No. That's only 60% of the planet has plate tectonics. The rest of the planet is continental. About 40% of the planet is continental and doesn't work through plate tectonics. It's affected by plate tectonics, but it doesn't lose its heat that way and doesn't get remade that way. It doesn't get created by plate tectonics. And when we look at Venus, as you'll see as we go on, we don't see plate tectonics like we do on the Earth. So there's something odd in terms of how these two planets work, and the connection actually is our continental crust. And that's something that I will come on to. But in lots of ways, they are very similar planets. Venus, of course, is very, very dry, so it has almost no water. But actually, in other respects, nitrogen, carbon dioxide, sulfur dioxide, other gases like that, it's got more volatiles than Earth does, Earth in the atmosphere, crust, and oceans. So it's a volatile-rich planet. It's got complex geology. This is a messy world. It's not easy to understand it, and that's what's thrown planetary scientists for years who've grown up trying to understand planets like the Moon, which are much easier to understand. And one of the things that's really hard to understand about Venus is its impact craters. So this is all of the impact craters on Venus, 942 of them. And they're scattered at random across the surface. Well, that is totally bonkers. That's completely at odds with the geology. The geology is complex. It's different in different places. There are, let's see, which way around does this work? Button at the back, button at the front, oh, button there. Right, there we go. It's got rift systems, it's got big volcanoes, it's got continental-like highlands, it's got vast plains, mountain belts, you know, really, really complex geology, and yet it has craters just at random across the surface. And not lots of craters, a few craters. 942 craters equates to about 500 million years age. About 730 is the best estimate to date for the average age of the Venus surface. So it doesn't have plate tectonics, but it has lots of tectonics. As I said, rift systems, mountain belts, etc. And it drives volcanism across the planet too. It doesn't have much in the way of obvious sedimentary processes, aeolian processes, but the atmosphere is like it's about a tenth the density of water. It's a gas, it's a fluid, it's not a liquid, but it behaves in many ways like the deep marine environment. And so if this works, which I might have to turn that back on. Is that going to come back on? Let's see. Let's see if that works. If this works, you should hear. So that sounds loud, doesn't it? That's the first sound recording from another planet. Venus has lots of firsts, actually. First picture from another planet, and definitely the first sound recording from another planet. But that is the sound of the lander, bang, dissipating out into that ocean, and you'll hear it just goes completely quiet. It is a very, very quiet place. There aren't any whales swimming around in that. It's so quiet you could hear, there'll be another one in a minute, the caps, the lens caps going off of the lander with a little bit of pyrotechnics so that the arms can go out and the camera can take its pictures and that sort of thing. And yet in other respects, despite being very quiet, Venus is very interesting. This is the first picture from another planet, and it's unlike any other. I'll turn that down for you, because that's the drill starting. That's what that's that noise. It's unlike any other picture from another planet. Actually, we don't see this anywhere but Earth. This is scree. It's colluvium. It's a slope. It was actually only about 20 degrees slope, but these are rock clasts. They're a little bit rounded. They've been rolling down that slope. This is evidence of geological activity on the surface. And actually, Don Mitchell, who got the original Venera data and reprocessed it all properly, brought out a lot of detail that wasn't obvious in the prints that were made. And actually, there you are looking down the valley at the other side. So there's a drop off is a graben, and that's the hills on the other side of the valley. And that's the sky up there because you're looking upslope. So remarkable. But most of Venus has this sort of flat, platey texture, rubble lying around all over the place. Venera 10, I think, is the next most interesting image. I might talk about that bit in the distance towards the end. And these are supposedly lava flows. They didn't look like lava flows to me. You were just wandering around. You didn't really properly have Yorkshire flags, did you? They were made into something else. But if you wandered around proper Yorkshire flag, it would look like this. It's shales and flags. And actually, the landers themselves, when they were first analysed, they thought they were sedimentary. The strength of the materials is sedimentary. The grain sizes are sedimentary. It's sediments made of basalt, probably, reworked and moved around, but not directly a lava flow, I would say. So most of this surface is very, very flat, and most of the surface of Venus, these plains, are very, very flat. So what is going on? I want to kind of recap this. I deliberately got a few slides in from the last time I talked here because I was going to quiz you just to make sure that you were paying attention last time. You did. So just to sort of recap where we are, this is Earth. This is the Hawaii Emperor Seamount chain. So this is something like 70 million years of volcanism. And each one of these was in Hawaii, was a big island at one point. They're roughly 1 million years apart. And the reason they're strung out like that is there's a plume coming up from the core, hitting the Pacific plate as it moves at 5 centimeters a year. And this bend is because the Pacific plate reorganizes itself when India hits Asia and everything changes. This is the same plume on Mars. It doesn't go anywhere. It's a static planet. So it just keeps creating the same volcano. And you can make Olympus Mons, which is the biggest volcano in the solar system, in about 45 million years of Hawaii. So when we look at these huge volcanoes on Mars, we're actually looking at not a volcanic world. We're looking at a very dead world. Venus is different. The volcanoes, they're oddly flat. They don't have a lot of topography. This one is actually about the size of the big island, and it's the one that's been shown to be active today, or at least when Magellan was there. But they're large, but they're not this big. And within an area of a plume, this is the Atla plume area, there are, I think, about 11 volcanoes, 10 or 11 volcanoes in that area. And they're slightly scattered at random. When one of Philippa's students did a huge amount of really detailed mapping and can show you how this plume evolved with time and which volcano came first, this one, and then how it moved around. And so this plume isn't moving around. It's not sort of zigzagging around. It's the plate on the surface is moving around a little bit. And it's moving around at about 1/10 of the rate of terrestrial plates. But that's still moving. And that's the kind of movements I've been very interested in engineering geology. And I've been talking about this for many years, and how Venus must have this kind of tectonic pattern to it, and kind of at odds with the Venus community at large, who believe in this catastrophic overturn and one plate planet and that sort of thing, because they can't get their heads around an active Venus. Where was I going with that? Oh yes, and then one day I was at a Venus workshop in Zurich, and a guy called Diogo stood up and he gave this talk about the early Earth. And he said, lots of people say early Venus is like the early Earth. This is his model of the early Earth before Earth had plate tectonics. And I won't go into all the details. He explained how it worked, but basically the surface gets broken into lots of small plates, and they get remade very quickly in sort of tens of millions of years or so, and jostle around. So you make these little blocks, and they kind of jostle around together. And this is exactly what I'd seen in London. And actually, as it turns out now, also in Melbourne in Australia and in China. This is the radar data that was alluded to earlier, and Tim asked me to put something of London in there. So I've taken out the China one, and there's the London one. It's beautiful. The data you can see. This is water coming up faults on a it's a inverting transtensional structure, so it's now transpressional. And there's the main strike slip fault here, which you can see they're dewatering this bit. But it's acting as a barrier there. And this side where they had dewatered docklands is now recharging, but it's coming up the fault line. So we can see all this lovely detail in the radar data. But the point is, this is how continents work on the Earth. They're basically, continents are broken into blocks. Don Cosgrove will tell you all about this. And those blocks nudge against each other, and that's what drives all our neotectonics here in Britain and elsewhere in Europe. And this is a much more bold example, if you like. This is the Tarim Basin in China, which is where I had the other image from. So these are really big mountains because it's part of the India-Asia collision. But you can see there's this block there in which I'm not moving. You do anything you want around the outside, but I'm not going anywhere. This is a stiff, big block. But it's only, what, 500-600 kilometers across? And that's the kind of block size we see on Venus. This is, in fact, the largest one we see on Venus. Most of them are smaller than this and are about that sort of size, but these are the same scale. This is newer in the equatorial region. This is the edge of Artemis Corona here. Rift systems running around parts of it, strike slip systems through here, and compressional systems and so on. And this is one of these blocks, and it's kind of nudging and rotating around and bashing into its neighbors. And this, it turns out, explains the craters, not the other way around. So for years, for decades, people said the craters are telling you that nothing's happening on the surface. It all happened in one go, and then the geology stopped. Well, in fact, the geology is telling you that we have 942 randomly distributed craters because we have 1,000 of these blocks all bashing together against each other. And if a crater lands here, it doesn't last very long, 50 million years at most. If it lands in here in the middle, it's there for 500 million years till another sort of boundary comes across it. And these sort of jostling plates predicted by the numerical modeling, observed in the Venus data, explain how Venus works. Now, I won't go into too much detail about why, except that basalt on Venus at 450 degrees C is a lot like granite on the Earth at 20 degrees C in terms of its mechanical behavior. So in some ways, it's not surprising that the crust of Venus behaves like the continental crust of the Earth. And if you imagine not 40%, but 100% continental crust on the Earth, this is what it would look like. So that's all well and good, and it explains a lot about how the planet works. And we can learn something about the history by looking at what we do think are true continental regions. It's only about 10% of Venus, not 40% as on Earth, and that's probably because Venus doesn't have plate tectonics in our sense to, accrete rapidly bigger continents, but it has the same kind of core regions to its continents that ours do. These are what I think are Archean core terrains in the continental regions, and around the outside you have mobile belt after mobile belt plastered onto it. So what's something that's quite interesting about Venus, and I think is a nice full circle, I do love a story that comes together in the end, is that when you start to look at how these blocks are arranged and on the surface and how they might be nudging into each other and everything, one thing you notice is that the rift systems are all to the south of these continental regions at the equator and kind of directed northwards, and all the blocks nudge into each other, and they all converge on this region called Ishtar up here, which is the highest point on Venus of this Maxwell Montes here, these mountains here. And this is a plains block that's been lifted up by about 4 or 5 kilometers. So everything is converging, and it sort of explains why Ishtar is the way it is, because it's all converging on it. And it turns out that that is telling you that the driving process on Venus for these movements is not the rifting. The continents aren't a passive conveyor like they are on the Earth with plate tectonics. They are actively drifting. So the keel of the continent is drifting in the mantle flow, and they're leaving a wake behind them, which is the rift system, and they're ploughing into the plains in front of them as they push northwards. So it sort of goes back to the original thinking about continental drift before we had plate tectonics, the evidence that we had for continental drift. And I like that. So Venus is the Earth as it was imagined to be at one point. But there is a problem, and this is probably where the ideas of catastrophic resurfacing may come from. There is a problem. Venus cannot lose enough heat this way. And actually, as it turns out, neither can Earth. It's just a bit more subtle on the Earth. And we do have to look back in time at evidence of what went on in the Archean to really understand what might be taking place on Venus today. And so this is a model from a chap called Jean Bedard in Canada, who is a very good cook and a very good drinker. Him and Lyle Harris, real good geologists. Lyle works for the Geological Survey, John works for the university. I'm pretty sure that's the right way around. And they did some research on, in detail on the Canadian craton to try and understand its history. And what they realized was the way it was constructed, and then they looked at the Pilbara and other places as well, was that it's not put together in the way a modern continent is. It's not accreted bits around the outside. The process is completely different and relies on something rather different going on in the Earth. And what they realized was that without modern plate tectonics, you can't cool the interior efficiently. And so what happens is that the sort of what they call hindered plate tectonics, but it's the same thing as we see on Venus with this continental drift and the Campi movement and so on, cools the outer part, the upper mantle. And that takes part in this cycle, and everything's fine for 500 million years. But the lower mantle is just heating up. It's not cooling. It's got a blanket above it. So the lower mantle gets hotter and hotter and hotter. It's got stuff coming out of the core, and it's got radioactives in it that are making it hotter over time, until locally, not globally, but locally, it overturns. And it does that in a very localized way, if you like, and I'll explain in a minute what it looks like. But you have what's called an overturn upwelling zone, or an ouzo, in which you get a whole series of plumes connected together, erupting material out, hot primitive mantled material out, reworking that part of the surface. If there's a continent there, it's destroyed. But if it's associated with it, it can actually stabilize the continent. And they think that's what happens to stabilize the Archean roots of the cratons that we have left. And it starts up, basically it mixes up this depleted mantle, the upper mantle, pushes it back down into the deeper mantle, and so cools the interior by that overturn. And this is something that actually is not confined to the Archean. Over time, the Earth is slowly getting towards equilibrium, but it isn't in equilibrium because 40% of the planet is not ocean, it's not plate tectonics. And if we wind the clock back about 100 million years or so, 150 million years, the color scale on here is the geoid. And so this bit is modern subduction. It's not really there, but the geoid takes a long time to re-equilibrate. And so it shows us what was going on actually during Pangaea. So this is Pangaea here. And you can see underneath all of Pangaea, it's hot. The geoid is high, it's coming up. And on the Antipodes in the Pacific and Panthalassa, you've got another high. And in between, you've got a big low. So these big things are coming up, and it's dropping down here just below Asia. And then you look at what happens. This rift, this whole continent starts to unzip all the way through the middle. So this is essentially the Atlantic Ocean. And then I haven't shown it on here, but there's the Indian Ocean, the Australian, Southern Ocean around here. And you can see why India moves so fast towards Asia. It basically races off downhill, down the geoid, zooms off into that direction and smashes into Asia. But this is an oozo. We don't think of it as an oozo because we're close to it in time, and we see it taking place over 100 million years. 50 million years, 100 million years. And we see it, we call it the Cretaceous superplume, but it's essentially an oozo. And we see the same sort of thing on Venus. In fact, actually, we see the same thing on Mars, which is really interesting. We see this bipolar symmetry where Tharsis and, forgotten the name of the other volcano, I want to say Iceland, but that's Venus. On the other side, there's a sort of smaller plume. You get this really big plume here in Lada and Iceland, and a smaller plume where Atla is. And we've mapped Atla in a lot of detail, and we kind of understand how it works. People have been mapping Iceland, and I've had students mapping Lada, and Lada is really interesting because this is like the continental breakup of Pangaea. There's bits of tesserae all over here, and it's just smashed apart, and there are huge volcanoes. This whole continent here is completely flooded in flood lavas, and it's got a volcano on it that I think is Mull, basically. Reminds me of Mull. The same sort of thing as the North Atlantic province. And elsewhere, you've got the continental roots. They obviously look blue in this with the ratio, but actually you've got, again, like with India, you've got this sort of deep downwelling zone here where something is going to go racing towards it, and that something would appear to be Artemis. Artemis is this really unusual feature here, and it's racing off in that direction, like rollback subduction or something like that. So something else that has changed over the years is that I've stopped ignoring craters. I ignored craters because I thought I don't understand them. They're at odds with the geology. Now I understand the geology and how the craters fit in. Actually, it turns out the craters are quite interesting. And a good friend of mine, Robbie Herrick, at Alaska, realized that not all craters are pristine. This is a nice, fresh, young crater. It's got impact melt in the bottom, which is this bright material here. It's got all this blocky ejecta coming out of it. It's even got melt that comes out. It looks like rivers, doesn't it? But actually they're not. They're lava flows, impact melt flows coming out from the crater. This is a very fresh crater, and around the outside it has a, well, you can't see it at this scale, but it has a dark halo around it, which is the fine-grained ejecta from the impact. And it turns out that actually only a few of the craters on the surface of Venus, about 150, I think, have these bright floors, have these conditions. Most of the others have dark floors. They're infilled, they have alteration. Volcanic infill is what Robbie thinks. A lot of them are intermediate. And so it turns out that if you look at only these craters, you get an age, the sort of youngest age, if you like, on the surface of only about 150 million years. So this is now a planet that's actually easily as active as the Earth. But what I realized you can do is you could take this and look at it statistically, because these have nothing to do with resurfacing. They're independent. Okay, so they're a kind of independent measure of the resurfacing of Venus, ignoring the volcanoes and everything else. And so you can look at it and say, what's the probability that some part of Venus has been resurfaced just based on the craters? And look at what you get. You get this big long line of really high probability of resurfacing, right where we see the upwelling being, and right over here where Atla is as well, where the other upwelling area is. And we get a few surprising areas, not in the continents, but actually in the plains, which have had nothing happen to them for 700 million years or more. But actually, the other interesting thing about Venus, and actually, as it turns out, about the Earth, is that most of it is generally active. Most of it is green. This is like 50-50. It's been resurfaced. So lots of ongoing volcanism all across the surface. Now, anytime you look at a map of volcanism on the Earth, they will tell you that it is confined to the spreading ridges and the subduction zones around the outside. And that's where the most active volcanism is. But actually, there's volcanoes right the way across the seafloor, thousands of them. And there are on Venus. There's 85,000 volcanoes on Venus, unbelievably. So this is it without the craters on, so you can see it a bit more clearly. And we have one other piece of data from Venus Express, which hints at this. So these blue bits are probably, can't say for certain, but they're probably granitic or at least not basaltic, something different. But the red areas, they're not all active, but the red areas imply young, fresh material. So recent activity, recent being a few million years, not 100 million years. So just in the southern hemisphere, we can see a wide distribution of activity across the surface over not that long a period of time. I then started thinking about sedimentary processes on Venus, and I realized I'm going to have to speed up a bit. And the radar tells you lots of information about the surface materials. Don't worry about what this means, the scattering modes and things like this. This is just how the radar is returned. Dielectric is something about the intrinsic electrical properties of the rocks, but basically the green areas are relatively fresh, the blue areas are relatively weathered, the yellow to pink areas are weird. They have a telluric metal frost of some kind. And you can kind of classify the surface into different regions, but basically about half the surface is relatively young, fresh basalts resurfaced, and half the surface is those old shales and flags and sedimentary rocks of some kind. And there's still ongoing sedimentary processes. We can see that in something called the Doppler centroid of the radar, which means the beam is bent slightly from reflectors on the ground at a low angle. And these reflectors fit a Hadley circulation in the atmosphere. So rising air along the equator and sinking at the poles, and the air drawing along the surface, giving you ripples on the ground. There are aeolian processes going on. These are not lava flows filling this valley here. These are talus slopes with finer grain material going down into the middle, and you can even see some ripples or dunes in there. Now this is Death Valley by radar. The same way, you get this really sharp boundary where you cross over from gravelly material into sandy, finer material. And we've seen exactly this kind of stuff. This is going back to Venera 9. It landed on or near Tessera, so it sees this kind of rough material on those slopes. And we see aeolian movements, wind streaks moving the talus around, and we see these finer grain material blown out across the plains and raining out on the plains. And we can see this extinction curve here from the landers as they came down about 2 kilometers, 1.5, 2 kilometers altitude. There's a dust layer. That's the same altitude that we see those wind streaks and things at the higher elevations. And on the plains, we see it rain out. These are ripples. So these really are sedimentary rocks. And we even saw some change in the wind over about an hour-long period on the surface from Venera 13. So there's definitely sedimentary processes going on. And I think this is why I was saying Venera 10 is probably, for me, the most interesting, because it landed near Tessera. And this is probably wind-blown sediment from that Tessera. But that is probably the Tessera in the distance. That's probably the continental rise up onto that Tessera slope in the far distance from the plain. So you're probably looking out at this feature here. And that's where my story would end until actually a couple of years ago. So now, I turned the sound off. I thought you might recognize, some of you might recognize this music. Yeah. Tales of the Unexpected. Something very, very unlike me happened. And I saw I saw evidence. There's been evidence of a past wetter environment. Adrian Jones here, I remember coming out to me at a conference, excitedly telling me all about it, and I kind of thought, that's really interesting, but I was very skeptical because in my mind, Venus had always been dry. It just never had water in the first place. I didn't believe it had lost its oceans. I just thought it never had them. And that was the reaction that they got. The Venus community was quite closed, shall we say, to new ideas. It was dominated by certain geophysicists. But actually, funnily enough, Mike Warner said to me when I was telling him about this, he said, never underestimate Adrian Jones. 90% of what he says may be wrong, but the 10% is pure genius. So I sort of had that in the back of my mind, actually. And another colleague of mine, Dave Waltham here, who's just retired from Royal Holloway, I've known for many, many years before I came to Royal Holloway. And Veronica Bray, who was a student originally at UCL and came to Imperial when I was there. We worked on these sorts of channels, and I had the idea that the atmosphere is like an ocean. So we looked at modelling these canali as particulate currents as in the atmosphere. But actually, it's really hard. You can make it work, but it's really hard. It's much easier if they are actually in oceans. So these are submarine. These fit submarine channels really well. But nobody listens to Brits because it's a community that's dominated by American scientists. So it took this chap, Michael Way, who was a really lovely guy from New York, to do some modelling essentially about exoplanets, but essentially the question being, if you put Earth where Venus is, do you get Venus? And the models say, no, you don't. There's something else going on. It's not just the Goldilocks problem. It's not just that Venus is too close to the sun. Venus, if it had oceans today, would have oceans today. I know that's an oxymoron, but they wouldn't lose them under Earth-like conditions. So something happened for either to have never had oceans or to have lost them. And then I realized I didn't have a photo of Eloise, so I put one in here because the other places I've given this talk, she's been there with her poster or giving her talk herself. But anyway, this Eloise was a undergraduate student at Royal Holloway, and in her first year summer said, I'm bored, I'd like to do something interesting. Can you give me something to work on? I said, go away and look at Venus. There's lots of interesting things to look at. Go and look at the planes because I think you'll find out a lot. And I was expecting her to look at the canali and things like that, which she did. But she came across these things, polygonal fractures, lots and lots and lots of polygonal fractures. And so the following year, she had various health issues, so she couldn't go physical mapping, so she went digital mapping on Venus, and she mapped out these polygonal terrains on the surface, and she grouped them into two main groups, but 3 categories in each. So the truly sort of polygonal ones at various scales and slightly more ordered parallelogram type ones. But the really interesting thing about these polygonal fractures is their size. They're several kilometers across. They range down to the resolution limit, which is about 100 meters, but they go up to several kilometers across. And she looked at a whole series of analogues, and the only model that had been put forward at that point was global resurfacing, big thick lava flows cool down and crack into polygons. They don't do that. They crack into polygons that are this big, or maybe this big, but they don't crack into polygons that are kilometers across. And there are a number of ways in which you can make these polygons other than that, but they are all sedimentary. And the only way to make really big polygons is underwater, in fact, in deep marine sediments. And they're known around the world. In fact, Joe Cartwright, who I know was at Imperial and in Cardiff and Oxford and all around, was one of the key people behind finding out about polygonal fault systems from seismic data in basins on continental margins and other places. And it's not really fully understood how they form as such, but essentially it's a dewatering process. As the sediment load piles up, the water comes out and the clays shrink, and you generate these fractures which become faults, which propagate up towards the surface. They don't quite make it to the surface usually, but sometimes they do. These are some in the Caribbean, and they make these furrows on the seabed. And these look just like the polygonal fractures we see on Venus. I'm not going to quiz you. Eloise did a quiz where she put 2 pictures up and said which one's Venus, and about 3 people got it right. It's pretty hard to tell them apart. What we can see also are that the smaller fractures, the smaller polygons, could be desiccation, they could be salt. There's a number of things they could be. So if Venus lost its oceans, it would then desiccate and generate salt flats that would reflect this larger polygonal structure, but with many, many smaller polygons. And this is an example from Lake Natron in Tanzania, in both radar and optical. Something else that then starts to fit into place is that the lowlands of Venus have wrinkle ridges on them, these funny small inversion type structures. And they're thought really to have been inversion structures in lava flows, but it's really hard to make them because they're strong materials, lavas. And these wrinkle ridges reflect gradients of fractions of a degree on slope. But you can make them if they're on salt. So that we think there's something like these salt walls and salt anticlines as the salt from the evaporates from losing the oceans, basically move down slope into the basins, and they occur in all the deeper parts of the lowlands. And in fact, actually, if you work it out, if the area they cover elevation-wise represents the hypersaline ocean, and you dilute that ocean to terrestrial levels, terrestrial salinity, then about 90% of the surface of Venus is covered in oceans about 1 to 1.5 kilometers deep. And those oceans include all the features, cover the areas where all the features that we see related to oceans occur. So these are all the polygonal fracture systems. These are the big long canali in the deep marine basins. These are the wrinkle ridges on the surface. And the continental areas stay high and dry away from it. And the nearest analogue we have really is the Messinian salinity crisis. And this picture came out just before we submitted this for publication. So this is one of these is Cyprus, and this is the Eastern Mediterranean. And you can see these hypersaline basins here, still with the briny water in it. All the polygonal fractures are all out here. They're not really showing on this image, but it's picture, but they're out there. We can see all the kinds of features that we see on Venus. So it does really look like Venus lost its oceans. The question is when? And this is when it gets really interesting and quite exciting. So go back to these craters. These craters must have formed after the oceans were gone. And if we add them all up, all these bright floor craters, where they are, we can get an age at which the oceans must have been gone by. But the other craters, they're much more interesting than just dark floors. Look at this one. This one's got a backwash into it of sediment. It's got sediment all the way around the peak area here. And the ejecta flows like a fluid away. This isn't impact melt, this is ejecta. And there's no blockiness to it, or very few blocks. It's all gloopy. So this is, I think, an impact that hit the sea. So this is a crater that formed when Venus had oceans. And then, you know, we've got ones in between, the intermediate ones, during that interval. And there are two different things we can do. We can add up the number of different types of craters and get a date. And we can also look at the crater distribution, size, diameter distribution. And both those things point to the same age. And they point to an age of 309 million years. That's when Venus lost its oceans. Don't know how quickly it lost its oceans, but they were definitely gone by 211. And they were definitely there 442 million years ago. So we go back to the Ordovician, Venus had oceans, looked just like Earth. We go to the Permian, really nasty on Venus. I think it was bad here, it was really bad on Venus. So we can picture this. Venus with oceans in the Devonian. So you can imagine fish, plants on the land. I mean, I don't know if there were, but it's entirely plausible. And then it all goes wrong. The oceans start to disappear. We have hypersaline seas in the end of Carboniferous and towards the Permian, until by the Permian, Triassic, dead, gone. And those old blue areas that nothing's happened to, we can see the oceans. This is what I think is really telling. So I was talking through this with a sedimentologist at Holloway one day, and he said, well, that's a wave cut platform, and these are cliffs. And these are streamlined islands where the currents have been flowing along the floor. And look, this is the canali channel coming out, or actually maybe a fluvial channel. These are drainage channels cutting down, and we actually worked with people in Canada and published on these channels being flash flood deposits as the oceans came to an end. And yeah, put that into kind of 3D. You see, you know, you could be walking on a beach with the tide going out. This is just draining away. Really quite evocative. And yeah, so one of my friends said, you should ask AI to show you what it looked like. Absolute rubbish, really rubbish. So instead I went to Wales. I think this is probably the best image of what evaporating oceans might look like on an orange planet. Yeah, strange. I found it quite sort of harrowing, actually, thinking about a whole planet sterilizing itself. I think that's quite a profound problem to come across. You know, it's one thing to say there were bacteria on Mars 3 billion years ago and it didn't last. It's quite another thing to say there were fish 300 million years ago and then it got cooked. Because that's not so far away from a long hot summer going on to being an even hotter summer and a hotter summer. So you might ask, why did it happen? And I think it's the ozone. So if we go back to the Cretaceous, we have our superplume on Earth, 10 times the amount of carbon dioxide that we have now or more. You do that on Venus when it's at that critical threshold, then you tip it over the edge. So that last ouzo, probably in Lada Terra, where it was 100, 300 million years ago, tipped it over the edge and it lost its oceans. And what's scary about that is that the sun is getting hotter all the time. And in 1 billion years, Earth will be at the tipping point that Venus was 300 million years ago. So there's a sobering thought. Not in my lifetime, but, you know, something to think about. Thank you.